Welcome to this explainer. Today, we're going to explore a hidden world that exists literally right beneath our feet. Think about it. Whenever we turn on the tap for a glass of water or pass by those massive agricultural fields that feed us, we're relying on a vast, unseen architecture that we almost never think about. We're going to dive deep into the fascinating mechanics of groundwater. We'll figure out how it's stored, how it actually moves, and perhaps most importantly, how our actions up here on the surface are permanently altering it. Now get this, even though it seems like water completely covers our blue planet, only about 1% of the total water on Earth is actually groundwater. Just 1%. To put that into perspective, it's an incredibly precious slice of the pie. And, as we'll see today, because it accumulates so incredibly slowly, in a lot of regions, it effectively acts as a totally non-renewable resource. To demystify how this whole hidden system works, here's our roadmap. We'll start with the hidden water world. Move into porosity and permeability, explore aquifers and water tables, look at tapping groundwater, discuss depletion and pollution, and finally wrap up with caves and sinkholes. Section 1. The hidden water world. Let's look at where this water actually lives. You see, groundwater doesn't just magically appear out of thin air. It originates from rain that percolates deep down into the soil. But because so much rainfall just runs off the surface, it takes years, sometimes many, many years, for that water to seep down and actually build up underground reserves. Oh, and here's a crazy fact. The actual volume of that groundwater decreases the deeper you go into the Earth's crust. Why is that? Well, the immense overlying pressure from all that heavy rock physically compresses the Earth beneath it, keeping any open spaces to an absolute minimum. Section 2. Porosity and permeability. Let's talk about storing and flowing. The absolute crucial starting point here is understanding porosity. Think of porosity as the amount of empty room inside a rock. It can range from practically zero all the way up to 50% of a rock's total volume. It dictates exactly how much water a specific rock can hold. And that capacity, it depends entirely on a few key things, like the size of the grains in the soil, the variety of those grain sizes, their shapes, and whether or not there's some kind of natural cementing material binding it all together. Now, directly related to porosity is permeability. But while porosity is all about storage space, permeability is all about flow. You can have a highly porous rock, but that doesn't guarantee you'll get fast-moving water. If the pore spaces are super tiny, the ionic attraction of the water molecules to the rock actually slows the flow down significantly because of friction. Because of this, deep underground, water might only move mere centimeters per year. It is literally a snail's pace. So the physical recipe for groundwater storage really comes down to how those grains are sorted. Well-sorted sediment with large, uniform grains creates fantastic, continuous open spaces for water. That's the ideal setup for holding and moving it. But imagine what happens when smaller, finer materials get in there and clog the gaps, or a natural cement fills those voids entirely. The water has absolutely nowhere to go. Ultimately, the geology completely dictates the hydrology. Section 3. Aquifers and water tables. Time to look at the underground structures themselves. An aquifer is simply a massive body of highly permeable rock or soil. Basically, you can think of it as a giant underground sponge. It stores water in two main ways, either nestled right between the grains of porous sediment or inside a vast network of connected cracks, fractures, and fissures within solid rock. On the flip side, if the rock is totally impermeable, we call it an aquiclude. And an aquiclude acts like an impenetrable underground seal. When we look beneath the surface, the ground is essentially split into two distinct layers. Near the surface, we've got the aerated zone. The soil there is moist, but the open spaces are mostly filled with air. But below that lies the saturated zone, where every single crack, crevice, and pore is completely filled to the brim with water. And that exact boundary line resting right at the top of the saturated zone, that's exactly what we call the water table. Usually the water table kind of mimics the surface topography. It rises under hills and dips down into valleys, at least in human environments. But nature loves throwing us a curveball. Sometimes impermeable rock layers or tight lenses of clay can trap water on its journey downward. This creates what's known as a localized or perched water table that just sits there entirely separate and completely elevated above the main water table below. Section 4. Tapping into groundwater. Let's explore how we actually extract this stuff. So sometimes an aquifer gets sandwiched between two of those impermeable aquiclude layers we just talked about. When this happens on a slope, the trapped water becomes highly pressurized. We call this hydrostatic pressure.
Now, if we drill a borehole down into that confined aquifer, and our drill site happens to be geographically lower than the highest pressure point, well, something pretty amazing happens. The water flows up and out naturally, entirely on its own, without us needing a single pump. That is the magic of an artesian well.
Section 5, Depletion and Pollution. Time to talk about the human impact. Okay, so what exactly happens when we treat this slowly recharging system like an endless bank account? Well, when our extraction outpaces that incredibly slow natural recharge rate, the local water table around the borehole plummets. This creates a steep, cone-shaped depression underground. As we pump the water out, we're actually removing the fluid pressure that was literally helping hold the rock and soil apart. Without that internal pressure, the deep earth physically compacts. The terrifying result? The land surface above permanently subsides. It just sinks right downward. And it's not just about depleting the volume. Our surface activities severely impact the quality of the water too. Raw sewage from leaking septic tanks can easily seep straight down to the water table. Now, there is a tiny silver lining here. If the ground is made of porous sands, that sand can sometimes act like a natural filter, purifying the water a bit as it slowly travels. But if the water flows through large open fissures instead, that sewage spreads completely unfiltered, remaining heavily contaminated.
It gets even more dangerous when we bring toxic waste into the mix. We're talking hazardous chemicals and factory runoff leaching from unsealed landfills and industrial ponds. When rain washes through these dumps, it acts like a toxic delivery system, carrying a poisonous soup straight down into the groundwater supply. Honestly, it poisons the whole well. This is exactly why strict modern engineering dictates that rubbish dumps absolutely must be located on sealed, impermeable ground that is completely void of any natural cracks or faults. Section 6, Caves and Sinkholes. Let's look at the huge macroscopic consequences of all this. When rainwater falls, it naturally picks up a little bit of carbon dioxide from the atmosphere, turning into a very weak carbonic acid. Over thousands and thousands of years, as this slightly acidic water slowly penetrates the joints in calcareous rocks, things like limestone and dolomite, it literally dissolves the rock away from the inside out. It carves out massive underground cavities and huge surface depressions. Geologists call this karst topography. This incredible chemical process yields some truly stunning results. As that mineral-saturated water finally drips into the open air of these massive underground caves, it undergoes a chemical shift. It precipitates calcium carbonate out of the water, slowly, very slowly, building up majestic stalactites hanging from the ceiling and stalagmites rising up from the floor. It's incredibly beautiful, but it relies on a very delicate balance. Because you see, there's a serious hidden danger lurking here. These underground cavities are naturally completely filled with groundwater. And that water isn't just taking up space. It provides vital hydrostatic pressure that physically holds up the heavy rock roof of the cave. When industrial operations, like the aggressive gold mining we've historically seen in parts of South Africa, continuously pump out this water to keep their mines dry, they strip away that structural support. The loss of pressure causes those cave roofs to violently collapse, tearing open catastrophic sinkholes right at the surface. So we are dealing with a magnificent, yet incredibly fragile system. Groundwater accounts for just a tiny 1% fraction of the world's water, and it takes anywhere from thousands to literally millions of years to build up in these aquifers. Considering the very real threats of irreversible depletion, toxic pollution, and collapsing landforms, how long can we really keep overdrawing this non-renewable underground account before the well runs completely dry?